All right, so hello everyone. I'm Amir Poolad, and welcome to the presentation about the memory consistency model of the Nvidia PTX intermediate representation. So, throughout the course of these slides, I'm going to talk a little bit about GPU basics, just to get on the same page. And then I'm going to talk a little bit about coherence and consistency in GPUs in general, and some history about how Nvidia did it. And then at last, talk about the PTX memory consistency model itself. So a GPU, it's consisted of many streaming multiprocessors, each of them having a lot of cores, called, I believe NVIDIA calls them CUDA cores. The basic SIMT unit is normally 32 wide, but it's not exactly standardized. And some GPUs, I think Intel and AMD, it could be a different number. I think Intel is like 16 at the moment. But it could be different. NVIDIA GPUs are, at this date, they're all 32 wide. And by SIMT unit, what I mean is you have 32 CUDA cores all running the same instruction. So this SIMT unit is called a warp in NVIDIA parlance, and all cores in a warp used to share the program counter. And it's still a very useful mental model to have. So so all the cores in a warp sharing a program counter, a very useful mental model, and we're going to work with it until we see how it works otherwise. So, and here we have the exact same thing I'll talk about. You have an L2 cache, a crossbar, and an SM with a L1 cache, multiple SMs, each with its own L1 cache. So, how to program a GPU? Programmers will group the threads into blocks. In PTX, they're also called CTA, which I forgot what they stand for. Each block of threads is guaranteed to run on a single SM. So this whole kernel is consisting of multiple blocks, and they get dispatched to a GPU. Each block is assigned to a single SM, and each thread is assigned to a single CUDA core.
So just a quick question.
Okay.
So the SM is just a collection of CUDA cores,
Yes.
all executing the same thing.
No. So an SM could have multiple warps in it.
I see.
Yeah, it could be like 1,000 cores, but they're divided into groups of 32 that are each called a warp.
I see. And then each warp, those ones will execute the same instructions.
Yes.
Basically, but like obviously they have different values inside those.
Yes, exactly.
Gotcha.
So, hi Juan. Coherence and consistency in GPUs, how did that work? So before GPU, general purpose programming on GPUs, the only workload was graphics. It's embarrassingly parallel. So on a graphics pipeline, the only programmable things we do are the vertex shader and the pixel shader. The vertex shader gets a bunch of vertices, which each is basically a point in 3D space, and transforms it into a different point in 3D space. An example that you might see in games is if you have blades of grass swaying around in wind. That's done in a vertex shader, actually. So the model for the grass itself is stationary. The GPU vertex shader applies like a sine function or something to the vertices in the grass blades, and it would seem like it's swaying around in the wind. And then you have a pixel shader that gets a pixel and decides what color it should be. So graphics programming, embarrassingly parallel, there's no need to have any communication between threads. And so, who needs a memory model? And there wasn't any memory model, actually. So enter GPU, and people are trying to do general purpose programming, and people want locks now. And there's a starvation everywhere. To see why this starvation and deadlock happen, let's see how thread scheduling with branches look like at this time. So here we have a piece of code. It says that if the thread index, this is the number of the thread in the warp. So you have 32 threads. It starts from 0 to 31. The first 4 threads execute A and B. The rest of them execute X and Y, and then they all execute Z. So what happens is all the threads, all the cores share the same PC. So all the cores, the PC is at A. The GPU just turns off the cores that are not executing A. And then the same thing with B. And then when we execute X and Y, we just turn the other cores on and the cores off. And when we execute C, which is all the cores are running again, and we reconverge. Basically, everything is running again. But this could result in a starvation. Let's see an example. This is we're basically trying to do some mutual exclusion problem. We do a critic job and we acquire a lock. So what happens when one of the threads in the warp acquires a lock? And now we have two divergent branches, but the scheduler for the warp decides to first execute the ones that don't have the lock and are going to spin forever. We have a deadlock. So here comes the Volta microarchitecture with independent thread scheduling. So before Volta, as I said, we have a program counter and stack and a call stack shared between all of the threads in a warp. And after Volta, each of the CUDA cores has its own program counter and call stack. We still have the SIMT execution, so all of the cores in a warp will execute the exact same instruction or won't execute anything, but the PC can change.
So what that means, if I may, is that if I had like some program, a set of instructions, some of those threads might be doing one part of the program while another at the same exact time, another will be doing other instructions.
Not the same exact time. They kept the SIMT model. So at one instance of time, every thread in a warp will execute only one instruction. But the difference here that actually is different here is we can kind of swap between the different branches in a instruction level granularity. So you might actually just some of the threads will execute A and then switch to some of the other threads will execute X. So before this, since everyone shared PC, you could not do that because the PC was in A and then it was at B and then it was at X and then it was at Y. So you had to go through the entire program to reconverge all the threads. Right now, some of the threads, the PC is at E, the other ones have the PC at X. But since we do want it to be SIMT, they will execute A, and we can actually schedule it to the other threads to execute X.
How are you defining SIMT here?
Single instruction, multiple thread.
I see.
Single instruction.
So a
That's
single
the
instruction
yes.
gets executed.
Yes.
Oh, at any point in time.
At any point in time, one instruction.
I see. So across the entire warp, if there's an add instruction in the instruction list, only that add instruction is being
Yes,
performed right now.
exactly.
I get it. That makes sense.
Yeah. So now that we can actually,
I don't think I get it still. I mean, I
Okay.
get like the SMIT, okay, so the difference between one shared PC.
Yeah.
And everybody's got their own PC.
Yeah.
But they all still have to be executing the same thing.
we can
What-
switch
so-
between the divergent branches in an instruction level granularity. So here we execute A, then X, then B, then Y. But before, what we had to do is A and B had to execute. We cannot stop executing A and B and do something in the middle of
So
it.
you install until all of them are done and then you advance the program counter for
Yes.
everybody. And then you go back and you do that other
Um,
branch, I guess, right? Or, but you advance the program counter.
Yeah.
If there was only one, right?
Yeah.
So you had to go through all of the ABs first.
Yes.
Okay, now I've got different program counters, but I can only execute one instruction at a time.
Yes.
Okay, so let's see, so you're saying a bunch of them are gonna execute, a bunch are gonna be suppressed, right? Their program counters advance. Is everybody's program counter advance?
I think so, yes. So like these threads, when A executes, the program counter gets advanced to B,
Right.
but they get masked off when
Yeah.
X gets
So
executed.
it's not visible, but they all
Yeah.
did that. Okay,
And so the difference here that avoids the deadlock, when one thread has the lock and the others are like spinning, we don't have to wait for the spinning to finish because it won't finish. We can actually schedule the one thread that has the lock to do the work and free the lock. So we avoid the deadlock here.
And this maybe I'm stealing your thunder here. What's the benefit of being SIMT? It sounds like it's really causing us a lot of problems here.
So they do talk about why they do it. I think it was something about like the memory access patterns and memory bandwidth, it's better with SIMT basically.
Interesting.
As opposed to what?
As opposed to like a CPU, so like everyone gets their own program counter and then execute truly in parallel, like multiple cores.
Oh, that would destroy your CPU. The usual comparison is to SIMD.
I see.
Right.
Oh, well, yeah.
Because
vector
SIMT is close to SIMD, but a little more flexible, but compared to a CPU, then you just can't go with the same kind of number of cores.
Gotcha.
It's so much more complicated, so.
And it did want the traditional workloads like the graphics stuff, the embarrassingly parallel algorithms. They did want it to work exactly as it did before.
I see.
Yeah, the difference in SIMT and SIMD is subtle. There is
Yeah.
a difference, and I always forget what the heck. I gotta look up the examples again, because they're pretty close, but they're not quite the same. Oh, okay, I gotta say it somewhere.
So now that we have data sharing between the different threads, and it's possible to do that, and it's easy to do that, what exactly is possible? We need to have a consistency model now. So Nvidia published the PTX consistency model at that time. So before 2020, before the Volta architecture, there was no model. Now we do have a model. And so the basic text of the model is this. Any two operations may appear to happen in no order or in different order to different threads. The axioms introduced by the memory consistency model specify exactly which contradictions are forbidden between the orders observed by the different threads. What it's saying is, simplifying it is, anything can happen unless we explicitly forbid it. And they don't forbid much. It's a very weak model. To get it easier to get into like the actual rules, I'm going to ignore some of the operations, mainly the fence operation. I'm going to just ignore that. You can see the full details on the PTX documentation, and I'll reference it at the end.
Just a minor question.
Okay.
You say unless we forbid it, is that the consistency model has
Yes.
a big document that says here's the forbidden, here's forbidden, here's forbidden, or
Yes.
is it at runtime they forbid certain?
No, the consistency model has it's like 5 or 6 axioms.
I see.
Where you say, oh, this order cannot contradict
I
that
see.
or the other order, and we'll get into it in the future. So some important PTX instructions that the yellow highlighted ones are the ones we really care about, except of course the fence instructions, which I don't want to get into right now. You have a weak load, and you have a relaxed and acquire load. So these are load operations. The store operations, it could be a weak store, it could be just a store, a relaxed store, and a release store. So acquire and release are basically for doing synchronization. They define these things called the release pattern and the acquire pattern for acquiring a lock and releasing a lock, and they have actual like rules to how these things work. We'll get into that. Scope could be CTA, GPU, or system. CTA basically talks about the block. So the block of threads that you spawn using CUDA or whatever. GPU means the entire GPU, and system means the entire system, including GPU and the CPU. So what it means is that you load acquire with the scope of the GPU or do it within the scope of the CTA, the block. And what that means, I'll get into it in a bit. So there's a lot of jargon to get familiar with, so let's get started. Overlapping memory access it means what do you think it means, but to simplify things, we define it as accessing the same address. So basically mixed size addressing and things that could just overlap but not be the exact same address. Let's ignore those for now and think it as accessing the exact same thing. Strong operation. A fence operation or a memory operation with a relaxed acquire release or acquire release qualifier. What this means is that weak loads and weak stores are not considered to be strong.
And I think you said you also have a regular loaded store that has no qualifier. Is that correct?
Yes, that's also not considered to be strong. Yeah. Then there's morally strong operation. It's the naming is not exactly the best thing ever. Two operations are said to be morally strong relative to each other if they satisfy all of the following conditions. They are related in program order, or as in they're executed by same thread. So if you have two loads in the same threads, they're strong relative to each other. Or each of the operations is strong and its scope includes the other operations. So if you have two operations in GPU scope, that's good. If you have one in CTA scope and one in GPU scope, they could be not strong relative to each other. So one of them might be in an SM and the other one might be in another SM, and those are not considered to be in the same scope. So the CTA scope limits this scope to a single block. So if the other instruction is in another block, they're not in the same scope, meaning that it's not morally strong relative to each other. We see an example of this later to see how it's relevant. And if both are memory operations, they overlap. It's the same address. So stores to the same location, stores and loads to the same location, they have to be to the same address. If it's unrelated addresses, we really don't care about any consistency between that. So, and there's a whole lot of ordering. Program order, what do you think of? It's basically the finished assembly, the source code of the PTX, that's program order. Observation order, and there's one caveat here. Loops and things are considered to be flattened, so the first iteration of a loop and a second iteration of loop, there's an order in between that. It kind of works the way you expect it to. Observation order, if a write is before a read in an observation order, it's a write is happens before a read in observation order if they're morally strong relative to each other and the read is reading the thing that is written. So I'm not sure, was that clear enough? Okay. And there's the causality order. Operation X precedes Y in causality order if X synchronizes with Y. What does that mean, synchronize? It means like a release, an acquire. These patterns synchronize with each other, and you can use barriers to synchronize. So these two operations are considered to be synchronizing. There's a lot more information about what exactly is synchronization. The fences get kind of involved in that too, but I decided to not talk about it here in detail. I can look at the PTX documentation to see more. Coherence order is a partial transitive order. Partial meaning that not everything has to be ordered. So basically, you might have two operations that have no relation to each other in the coherence order. And it's transitive, meaning that like if A is before B and B is before C, then A is before C. Two writes are related if they are overlapping, related in the coherence order if they are overlapping, and they are morally strong or related in causality order. So basically, if we have a synchronization, we want the coherence to happen, and if they're morally strong relative to each other, we do want the coherence to happen also. Axiom of coherence. If a write W precedes and this is the first axiom, so the PTX consistency model is a bunch of different axioms that disallow some orderings. Axiom of coherence. If a write W precedes an overlapping write W prime in causality order, the causality order was talking about like synchronization. So if you synchronize something, then W must precede W prime in coherence order. What that means is basically not a lot, to be honest.
It basically, I think, if I'm understanding it correctly, I think it's basically just saying, if a write's writing to a memory address that the other one is also gonna write to, then everyone else must recognize that W prime was the actual last write, I think.
So this actually like I think this axiom is something that is actually given meaning to by the other
I see.
axiom. So this one is kind of abstract in of itself.
Okay.
So these are two abstract orderings, and now we say that, oh, these orderings must be like that. But what it actually means, the other axioms kind of define that better.
Cool.
Communication order is about the visibility of operations to each other. So W is before R if R returns the value of W. So if the write is visible to a read, we say that it precedes the read in communication order. Or a write precedes another write if the write precedes it in coherence order. So what that means is, yeah, so you have two writes and The coherence order says this happens before the other one. The visibility of those writes also happen in that order. A read precedes a write if a read precedes a write that happened before that write in coherence order. Single copy atomicity, this is another axiom. For a morally strong read and write, one of the following can happen. Either you read from that write or you read from a write before it in coherence order. What that means is if you're reading 4 bytes, you can read 2 of them from one write and 2 of them from another write. It's telling you that, okay, if you have a read, it's atomic. You will only read one single write. You won't read 2 separate writes, which is something that's expected, I guess. The more important part of the atomicity axiom is for the atomic operations. When an atomic operation A and a write W overlap and are morally strong, only one of these two can happen. The atomic operation reads any byte from a write W prime that precedes W in coherence order, or A follows W in coherence order. This is a bit hard to think about, but what it means is basically atomic operations do not happen in the middle of a write. All the writes in a system either happen after the atomic operations, completely after the atomic operations, or they're completely before the atomic operation. So if you have an atomic operations, it works the same way you expect it to, but only if they're morally strong. As an example, we have 2 increment instructions. Is it the visibility good here?
It should be fine.
Okay, yeah. So we have 2 increment instructions. So you read from the address X, put it to R0, add 1 to it, and then put it back into the since these two are morally strong relative to each other, they work the same way we expect it to. So, the final state, the X should be 2. So it started 0, and we incremented twice, it's 2. Now, for another example, these are in one of them is in CTA scope, the other is in GPU scope. So if this is in a block and this is in a different block, these two are not considered to be morally strong relative to each other. This axiom does not apply. So you could have a final state of X equals 1. So if you don't have morally strong atomic operations, they would not work as you expect it to. In a single sentence, morally strong atomics behave as you expect. That's basically the gist of the previous axiom. The axiom of sequential consistency per location. For overlapping morally strong memory operations, communication order cannot contradict the program order. What this means is that the program order, let's go with example, I think it's a bit more clear. So here we have thread 0 doing a store on address X, stores 1 into address X. Thread 1 reads from address X twice. These 2 instructions, the strong store and the strong load, are morally strong relative to each other. And these 2, since it's in the same thread, they're also morally strong related to each other. So what it's saying that if R1 is 1, if I read 1 here, then this store is visible at that point. So for the load week, for the second load, it should also be visible. So you cannot read 0 here. Any questions about this?
That is a little different than a CPU, actually. So what they're saying is that if a morally strong, 2 morally strong operations occur between 2 threads, and you yourself are morally strong with what previously happened, you can trust what previously happened in X.
In the program order, visibility is always okay here. So in the program order, we have first this is strong load and then the weak load. If it's visible by the strong load, it will also be visible by the weak load. But if this strong load reads 0, this could read 0 or a 1.
Yeah.
Another example. So if you have a strong store and in one thread and two stores in another thread, again, these two first instructions are morally strong relative to each other, and the last and the two in the thread 1 are also morally strong relative to each other. What this means that, oh, sorry, this is a load. If I'm loading a 1 here, meaning that this X is visible, so this X has already happened, and I'm loading a 1 here. This store will definitely happen after this other store. So you cannot have a memory address of 1 here. Basically, if I'm reading a 1, this has already happened. So when I'm storing a 2 in there, this happens after that other store. So it should be a 2. In another example, it's a write-read coherence. I have a strong store, another strong store, and a weak load. Again, same things happen. These two are morally strong relative to each other, and I have a weak load here. If the memory address is 2, this means that this happened after the other store, right? So this is this already yeah. So when this happened last, this read should also be reading from that last write.
And just so I can confirm, so a possible ordering that's impossible is it, could I do the right store? I store a 2 to X,
Okay.
and then I store the 1, and then I do the weak load. That's impossible, is what you're saying.
No, that is possible.
But that's a forbidden outcome, because then R1, oh, what's in?
No. The address is 2. So the very last store that happened is 2.
Right, but isn't that a store, like, if I store a 2 on the right,
Okay.
then I store a 1 on the left.
All right.
Then I load weak, wouldn't R1 now hold a 1?
It would hold a 1, but X would also be a 1.
Oh, yeah, I
Right.
get it.
Yeah.
Thanks.
And then write coherence. We have 2 stores, and the final outcome, the X should be 1, obviously. So, this is something that we definitely expect to happen.
What a basic question. What does CTA stand for again?
CTA is so CUDA blocks are called CTA in PTX. I'm not sure why they name it differently, but that's what it is.
The block. Okay.
Yeah.
What's the definition of a CUDA block?
I can go back to the
Oh, that is this beginning one.
yeah, kind of.
Sorry.
So no problem. So we have these SMs. Each of them could be containing like thousands of cores.
So I know those.
Yep. A CUDA block is a bunch of threads
Okay,
that
so it
definitely
just
get
means
assigned
thread
to
block.
a single
Okay.
SM. Yeah.
So CTA is thread block. Got
Yeah.
it.
No thinner axiom. This is mostly for reasons of mathematical consistency and proving. It means that you can just speculate values from thin air. So if this axiom wasn't there, and the final outcome of these was both registers would be 42, none of the other axioms would be violated. But this is definitely something that we don't want it to happen, right? So we load address Y to R1 and we store it at X, and then we load X to R2 and store it at Y. If this axiom wasn't here, meaning telling it that, hey, we can get values out of thin air, none of the other axioms would be violated if they just got some value 42 out of nowhere. Yeah, just kind of theoretical edge case solving. Yeah.
So, if you are like a programmer, are you the one declaring like should this load be weak or strong? And you would have to follow them all and write it this way.
If you're writing PTX, you will do that. Yeah. So the instructions look exactly as they do here. So you would write st.strong.gpu. When you're writing CUDA, the MVCC does that for you.
And so to whose benefit is all this memory consistency then?
If you're doing the embarrassing parallel stuff, not doing any kind of synchronization, you could just use weak everything and have zero memory consistency, zero cache coherence penalty, no traffic, great performance. If you do want synchronization, they gave you some rules. You can work with them to kind of work something out, have some synchronization going on.
Interesting.
Yeah. The causality axiom is talking about like kind of making synchronization actually happen. Relations in communication order cannot contradict causality order. So if a read R precedes overlapping writes W in causality order, then R cannot read from W. Meaning that if we synchronize the read and writes, the actual result of the read and writes would be as we expected, the synchronization would happen. And if a write precedes a read, then the read cannot read from any other write that happens before the write we talk about. In simple words, if we synchronize, the synchronization actually happens. It's a bit of a, it's a very axiom. So the wording gets a bit complicated, but that's basically what it's talking about. Now, here's the full list of axioms and the actual wording, the full wordings. There's another axiom called the fence SC axiom, which talks about how fences behave, but I kind of ignore fences because it would make everything just a bit too complicated.
It looks like a tax law document.
Yeah. Yeah, the actual document is quite hard to read, so yeah. And so in conclusion, with weak operations, anything goes. So you don't have any performance loss for traditional workloads. So you're doing graphics programming, you're doing matrix multiply stuff, you're doing embarrassing parallel algorithms that don't need synchronization. You don't pay any performance penalty for that. Using strong operations, you have some guarantees defined by these axiom that makes these new workloads that need locking and synchronization possible or easier. So doing locking was possible before Volta, but it wasn't really easy to do, and it wasn't really defined anywhere. So Nvidia could just make some new GPUs that your algorithm just completely didn't work with them. But now you have a memory model. If you abide by it, if you use it, then it's kind of guaranteed to work. My reference is the paper by Daniel Lustig and the CUDA programming model, the documentation for the PTX ISA, and the white paper for the Volta architecture. And the Volta architecture is like the data center version of the Turing architecture. The Turing is the RTX 2000 series where they introduced the tensor cores and the ray tracing acceleration stuff. And yeah, thanks for listening to me. And do you have any questions? Okay. I can't see comments here.
I'm just checking.
How would I do that? Oh, okay, I found it.
We'll get in chat.
Yep, okay. All right.
Yeah, I do have a quick question. So, this is probably for like hardware engine or like the hardware designers. They are promising that when you write this PTX, I promise you that your memory won't get squashed because you follow these rules. Is that kind of what's going on?
Basically, and also like for CUDA, they introduced this concept cooperative groups, I believe. I think it's called something similar to this. They give you this ability to synchronize between threads, like in various degrees of granularity. So you could synchronize between different threads in a warp, or different threads in a SM, or different threads in between SMs, between GPUs even. And so the way they actually do that is using these weak operations and fences and barriers and things we talked about.
Super cool. Any other questions? Well, thank you all so much for joining us today.
Well, thank you.